Hello everyone, we're going to be looking at 2.8, which is related rates and their word problems, and they're pretty good. And so here's the, uh, so on these related rate problems, we'll be finding the derivative with respect to time. And, um, and so remember when we were taking the derivative with respect to x, when we took the derivative of y, we had the derivative of y was dx. Well, now that we're taking the derivative with respect to time, if you take the derivative of the, I guess this is volume, isn't it? Of the volume, that would be dv dt. So if I take the derivative of v, it would be dv dt. Pi is a constant, so I'll leave pi right there. And then I would be taking the derivative of r and the derivative of h. Since they're being multiplied together, I'd have to use the product rule. So my u would be r squared, and my v would be h. So that v prime would be dh dt, and u prime would be 2r dr dt. Now, because I have my pi out here, I feel like I need to move this down a little bit so it'll not go in there. This is actually take 2 of the video, so I'm erasing over erasing. The first video, I was almost done with it and got a very important phone call that I needed to take, and it's almost faster to start again than it is to try to edit them together. So, and so the product rule, r squared times dh dt plus, and then 2r times h, and then times dr dt. So 2rh dr dt. So I had 3 variables, v, r, and h. And when I took the derivative with respect to time, I'm going to have a dv, I'm going to have, each one of them is going to have a rate, right? So I had v, so I have, in the derivative, I have dv dt. I had r, so in the derivative, I have dr dt. And I had h, so in the derivative, I have dh dt. Anyway, okay, so that was just a little practice of taking the derivative. You can multiply the pi if you wanted, or not, whatever you want to do on that was good. So these related rate problems, what you want to do is you want to read the problem all the way through a few times, list things that are known and unknown, and use proper notation. And what I mean by proper notation, if x is a distance, then dx dt would be the velocity. So if they start talking about a velocity, you should be writing something like dx dt for that velocity and naming it that way. If v is a volume, then dv dt is the rate that the volume is changing. So if they tell you the rate that a volume is changing, then it's dv dt. What does the problem want you to find? Label with proper notation. So this proper notation is it's key. It really helps you put things together. Sometimes it's helpful to draw a picture. Sometimes it's helpful to use a formula. Sometimes like an area formula or the Pythagorean theorem or similar triangles I've seen. All of those kind of things. And sometimes it's helpful for me to write things in my own words, and I call that pseudo algebra because I start writing, plus signs when it was add or whatever have you. Big hint: don't replace variables with numerical values unless the value does not change from time start to time end. And so you might notice that they'll tell you find yada yada when blah blah. And so if it's not a constant all the way through, then you cannot put that number in until after you've taken the derivative. And then making an equation, use as few variables as possible. Remember, if v, r, and h are in your equation, then your equation in your equation, then dv dt, dr dt, and dh dt will all be present after you differentiate. And so if you don't know all of those things, then certainly you don't want to have an equation that has all those variables in it. And then you find the derivative with respect to time using the chain rule. So we were using the chain rule up here. So when we said that the derivative of r squared was 2r dr dt, we were using the chain rule, even though I know that we've probably practiced it enough that you don't even think of it as chain rule anymore on that. Evaluate and solve the problem. Check your answer doesn't make sense. And answer the question asked by the problem and use appropriate units. So this is problem 2a, and it says if A is the area of a circle with radius r and the circle expands as time passes, find dA dt in terms of dr dt. So the area of the circle is A equals pi r squared. And so this one is just kind of almost like that other, is they're just wanting me to practice finding the derivative, and then they kind of give me a problem that's going to use what we just did. And so now I'm going to find the derivative. Find the derivative. So I wrote this equation, derivative, with respect to time. So when I take the derivative of a, that's dA dt. And pi is a constant, so it holds still. And then when I take the derivative of r squared, that is 2r dr dt. And then if I just make it look just a tiny bit nicer, then this would be dA dt equals 2 pi r dr dt. And now I've done what they asked me to do, which is they wanted me to find an equation that had dA dt in it, starting from here, and dr dt in it. And there it is. And so that's all they wanted me to do. Then this one says, suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meters? So we kind of have a oil spill, and they said that it's circular. And as time passes, that spill is getting bigger, they said, and bigger. And so I just kind of wanted to show you that as time passes, that's getting bigger and bigger. And so I just kind of drew the three, this is, maybe at a certain time it was a small oil spill, and at a time a little bit later it was a little bit bigger oil spill, and a little bit bigger than that it was expanding, growing and growing, right? So they want to know, so that's kind of what's happening there. They say if the radius of the oil spill increases at a constant rate of 1 meter per second. Now they're talking about the radius increasing at 1 meter per second. So the radius is r, and so if we're looking at its rate, that would be dr dt. And I just want you to notice here this, and they said this was 1 meter per second, and notice that the radius is in meters and the time is in seconds. So that kind of helps too, that hey, the units should go with this. Now the question that they're asking, this is what they're asking us to find. I'm going to say this is the question. It says, how fast is the area changing? How fast is the area of the spill increasing? And so now, because the radius was increasing, the dr dt was positive. And they're wanting us to know how fast is the area of the spill increasing. Now that's also a rate, and you would write a rate dA dt. That's what they're wanting us to find. I put question, Q for question. I meant to say this is what they want me to find. So I'm going to say find dA dt. And then they said when the radius is 30 meters. Now, is the radius always 30 meters? And so here's the radius of the oil spill. So this is at a certain time. And then a little bit later, that radius is bigger. And then a little bit later, that radius is even bigger yet. And so is the radius of the oil spill always 30 meters? And the answer is no. So that means that this number cannot be put in until after you find the derivative. And so because it's a circle, and they kind of led us through that, then we would start off with a equals pi r squared. And then we would find the derivative with respect to time, and we would clean it up, and we would get to this, right? And then you notice that they're asking me to find dA dt. They've told me dr dt, and they've also, and I've found the derivative, so now it's okay to plug in r is 30. And you notice if I do that, I'll be able to find dA dt. So from my work above, so if I hadn't had this work above, I would have been writing all of this right here. But since I did have it, I can just go up there and use it. dA dt equals 2 pi r dr dt. And we're going to be plugging in, so dA dt equals 2 pi, r is 30 meters, and dr dt is 1 meter per second. And so if we multiply that together, they wanted us to find dA dt. If we multiply that together, we'll have 60 pi meters squared per second. And so we're math people, and so this is a good answer. And if they wanted me to round, they would have told me, hey, round, and I would have gladly put in pi to be 3.14. And okay, we're going to try the next one and see how we do. This one also came out of your book, and I'm not sure which number it was now. I named it example, and maybe it came out of your book, and then they changed up some of their problems, and maybe I just loved it so much I left it in there. I'm not sure. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. How long is the ladder? So I have here, I just happen to have a nail, and I'm going to say that's my ladder. And I happen to have, so this just things I have here. I guess it's it's distracting no matter what. But here's my ladder leaning against my wall. Of course, my ladder is not going to lean against my wall without my hand holding it there. And this ladder is sliding. So as that ladder slides, it's going down the wall. And I was trying to get my hands out of the way so that you can see. And the bottom of the ladder is going away from the wall. So at first, the bottom of the ladder is close to the wall. And as it slides down the wall, the bottom of the ladder is going away from the wall. So that's kind of what you have going. And so I'm wanting to make a little picture of this. I'm going to draw the wall right here, and I'm going to draw the ladder right here. And here is the ground. So that right there is the ladder. And what's happening, this ladder is sliding down the wall. And so as it slides down the wall, it's kicking out away from the wall. Now the ladder doesn't change how long it is. The ladder is a constant length, but this distance right here as the ladder slides down the wall, that distance is decreasing. And as the ladder slides this way, right, as it slides down the wall, this distance right here from here to the bottom of the ladder is increasing. And in fact, they told me at what rate, that means I need to write it as a derivative, that it is sliding down the wall, and at what rate that it is sliding away from the wall. And so I'm going to name this distance right here something. You could call it whatever you want to call it. I'm thinking about calling it y. And I'm thinking about calling that x, is what I'm thinking of calling it. So then they have told me dy dt, that's sliding down. So this distance is actually getting smaller. And so this is going to be negative because that distance is getting smaller, 0.15 meters per second. And then dx dt, they also told me that. They said that that was 0.2 meters per second. And that one's positive because as the ladder slides down, this is actually getting longer, getting bigger. Okay, so now I need, and it says when the ladder is 3 meters from the wall, and the bottom of the ladder. So this is the bottom of the ladder. And so that we're finding this when x equals 3 meters. But x is not always 3 meters because that ladder is starting off, kind of upright. And as it slides down the wall, it's becoming, until it hits down. And so x is actually changing. Okay, so that's kind of our story there. Now, actually, they asked us to find the length of the ladder. And they're wanting us to find the length of the ladder when x is 3. Now, the length of the ladder is the same no matter what x is, but when x is 3, if I knew what y was, then I would be able to find the length of the ladder. If I knew what y was at that moment, I'd be able to find the length of the ladder without doing any calculus, right? I would just use the Pythagorean theorem. And so now I want to come up with an equation that I might be able to use in order to find the length of the ladder. And so equations that I have that go with triangles, like the area of the triangle is 1/2 base times height. And in this case, the base is x and the height is y. But that's not helpful to me because even though it has x and y in it, if I knew y, I'd be done with this problem. So even though I can say that this is 1/2 x times y, I'm not going to be able to use that to find y because I don't know anything about the area. If they had told me dA dt, I would be saying, oh, well, maybe this will be helpful for us. But I don't need to know dA dt. I don't know dA dt. And so what I want to find out is what y is what that would, I want to know the length of the ladder, but if I knew y, I'd know the length of the ladder. And so the other thing that you might be thinking of, this is a right triangle right here, and that is the Pythagorean theorem, which in this case is x squared plus y squared equals L squared. And so I'm looking at it to see, well, would that be helpful? I kind of put these equations up there. I also have some other triangle equations that I don't have similar triangles here. I was almost thinking, because I know some of the problems are similar triangles as well, but this one doesn't have 2 triangles. So, but I was thinking, would that be helpful? And so if I took the derivative with respect to time, then I would have dx dt, which I know, and I know x. I would have dy dt, right, which I would know. You could imagine you would also have y in the equation. And then I was thinking at first, the first time I did this problem, I was thinking I would have dl dt, and they didn't give me that. And so, and remember, we already talked about that if we knew y, we would know l immediately, and that's what they're asking us to find. But I was then realizing, wait a minute, let's talk about the things that are changing. Those are things that are variables. So is x changing from the time the problem starts to the end? And the answer is, remember that this ladder is sliding, and so yes, x is increasing. Is y changing? Yes, it is. Is L changing? No, it's not. L is a constant. At the beginning of the problem, L is the same length, the length of the ladder, as it is at the end of the problem. So actually, when you take the derivative of L with respect to time, because L is a constant, it's zero. The derivative of it with respect to time is zero. So I'm not going to have dl dt in my problem and have to worry about it. And so, good news. And so I think actually that this equation is going to be helpful. So I'm going to write it here to use. And then I'm going to take the derivative, find derivative. With respect to t, with respect to time, right? So when I take the derivative of this, that's going to be 2x dx dt plus 2y dy dt equals 0. And the only unknown I have is y in there. And that's good news because we already talked about that if we knew y, we would know the length of the ladder. And that was what is being asked of us. So I'm going to plug all this stuff in. Now that I've found the derivative, I'm going to plug in so this is 2, and then x is 3 meters. And then dx dt is 0.2 meters per second plus 2y, which is unknown. And then dy dt, negative 0.15 meters per second equals 0. And I think that we could, this is, the units here are meters squared. And if y has the unit meter, then this would be meters squared per second. I missed the per second here, but meters squared per second. And so I think when I get my calculator here, I think I will allow myself not to put the unit, since I know, hey, y is going to have meters as its unit, and then I won't have to worry about it. But I have that kind of here, and I kind of verified. So here I'm going to have 2 times 3 times 0.2. So that's 6 over 5, which is 1.2, plus, and then 2 times 0.15, and that should be negative. So this is negative minus 0.3y equals 0. I'm going to add the point negative. I'm going to add 0.3y to the both sides of the equation so that I can solve this. So when I add that to the other side over there, I get 1.2 equals 0.3. I'm going to divide by 0.3, and I get 4 equals y. Now that's not the answer, right? I put a box around it, so maybe I shouldn't have put a box around it, since that's not the answer. But I was so excited because I knew that, hey, once I found y, I'm going to be able to find L. And so it's that right back up here, right? X squared plus y squared equals L squared. And that would be for any given moment. And so at the moment that we are 3 meters, x is 3 meters, y is 4 meters, and we'll be able to use that to find L. And I hope you're saying that it's a 3, 4, 5 right triangle. And it definitely is. But if you needed to, you could be x squared plus y squared equals L squared. So if you didn't recognize that, So that would be 3 squared plus 4 squared equals L squared, which is 9 and 16 is 25 equals L squared. And so indeed, L is equal to 5. And in fact, that's 5 meters is the length of the ladder. I think that's a pretty long ladder. Okay, so we did a good job on that one. This one's draining a water heater. A water heater that has the shape of a right cylindrical tank has a radius of 1 foot and a height of 4 feet and is being drained. How fast is the water draining out of the tank in feet cubed per minute if the water level is dropping at 6 inches per minute? So something that's cylindrical shaped is like my teacup here, which my tea is getting really strong because I didn't take out my tea bag. But my teacup, my teacup there is cylindrical, and this has got water in it. My teacup's got tea in it, but it's got water in it, and they're draining it out. So I'm going to kind of draw a little picture of this. And I'm imagining there's a little spigot here at the bottom, and the water is draining out of it. That looks really bad, my drawing, but anyway, that's my water heater in my garage has a spigot at the bottom so that you can drain the water out. Now I noticed that they wanting the answer. They said, how fast is the water draining out of the tank in feet cubed per minute? And I noticed that that's in feet cubed, and this is in feet, and that is in feet, which is all very good, but this is in inches. And so I think that what I think that they're I think I need to turn that into feet, and then everything will be in feet. And because you can't have two units running around. Remember that 12 inches is 1 foot, so 6 inches is half a foot. So I'm gonna write this instead of as 6 inches. I'm gonna write this as 0.5 feet per minute. And then now I'm going to start to label out all of the stuff I have. You'll get used to this because there's quite a few problems where you're draining out something out, and like water out of a tank or whatever have you. And you notice that the units on that water being drained out are feet cubed. And I don't know if you recognize that the units that go with feet cubed are volume. And so right there, when they ask us how fast is the water draining out of the tank in feet cubed per minute, they're asking us to find, I guess I'll put that, find dv dt. That would be in feet cubed per minute. Now, what other things have they told me? They said a water heater that has the shape of a cylindrical tank with a radius of 1 foot. So I'm going to come in here and I'm going to draw the radius right here of 1 foot, and a height of 4 foot. So this is the height of my tank. I'm going to go right here and to right here, and that is 4 feet. The height of my tank. How fast is the water draining out of the tank in feet cubed per minute if the water level is dropping 0.5 feet per minute? Now I'm going to draw, I had a blue pen to draw the water in here, but I'm going to have to use purple, which is probably why you're draining your water heater, is because the water has become all rusty. And we'll say that purple is a rusty color. So there's my water in my tank. And that's the volume of water that we're talking. And since it's draining out, this level, the height of the water is, here's the height of the water, and the height of the water is falling. And so as I as the problem moves along, the maybe the water was completely full at the beginning, and as the water drains out, the height of the water is falling. And I'll ask you this: is the radius of the water changing? So here at the beginning, the radius of the water, and as the water drains out, is the radius of the water changing? And it's not. And so just so we kind of know, H is changing. That's the height of the water. But R is constant. That means if you know the value for R at the beginning of the problem, since it's the same as the value for R at the end of the problem, you can put it in. You can plug in that number right away. Or you can tell yourself that it's a constant and treat it just like a constant and not as a variable. So can you think of any equation that goes with volume of a cylinder? Because we're wanting to find dV dt. And you can look it up if you need to, but it's volume equals pi r squared h. And that was actually the one that we took the derivative of at the beginning of the problem. But in that problem, the very first thing that we did, in that problem, V, R, and H were all things that were changing. V is changing too, right? The volume is decreasing as time goes on, but R is constant. And so that was different on that first problem that we did. They were all three of them were variables. But since R is a constant, it's okay to go ahead and plug in what R is right now. And so they said, I want to make sure that they're saying the radius is 1 foot, and they are, and not the diameter is 1 foot. You'll see that a lot too. But here the radius is 1 foot. Is the height of the water 4 feet? And the answer is no. It might have been 4 feet at one time. The water heater is 4 feet high, but the water in the water heater is actually decreasing along. Okay, so I'm going to go ahead and plug in that one right here, 1 foot, and then squared h. And so I'm going to not write these units here now that we're done here. This is feet squared. If h was in feet, then that would be, the volume would be in feet cubed. And so I'm going to just write volume equals pi. Now 1 squared is 1, so this is just pi h. This one got pretty simplified, didn't it? Now I haven't taken the derivative yet, so now I'm going to find the derivative. Find the derivative. So the derivative of v is dv dt. Pi is a constant, so it holds still. And the derivative of h is dh dt. And they told me that the water level was dropping at 0.5 feet per minute. And I got so excited taking my derivative that I haven't even labeled what that is. But this is the water level dropping, and h is the height of the water. And so this is actually dh dt. And I'm going to put negative 0.5 feet per minute because it's dropping. And so this is dv dt equals pi times negative 0.05. Now I lost my units right here. That was feet squared, right? And I said that, hey, I'm gonna, and here would be feet per minute, right? So I stopped writing those units that I had right there because it was 1 squared, and that would have been feet squared. And I said to you that, hey, that that this is going to be feet cubed per minute, and you can see that it would be because here's feet squared, and then dH/dt is feet per minute. So I'm just going to go ahead and write this as feet cubed per minute. And so dV/dt, I almost want to, that's 1/2. So I'm almost wanting to write negative pi over 2. That seems good, right? 1 over 2 is half. Is that okay? Feet cubed, just because it's so nice. And, pi over 2 is one of my friends. And so that's the volume is decreasing at that. Now, if I don't get real particular on this, but I mean, it's negative, but if you said that it was decreasing, you could say that it was decreasing at pi over 2 feet cubed per minute. Or you could say that it's changing at negative pi over 2 feet cubed per minute. And then the negative tells you that it's decreasing. And so they asked how fast is the water draining out of the tank. And so I think because of the way the question is asked, how fast is it draining out of the tank, that I could answer pi over 2 feet cubed per minute. And like I said, that, yeah, the negative just tells me that it's draining out, right? And so if I want to say draining out, drain out, draining out, then that implies that it's decreasing, I guess, the draining out. So I don't have to put the negative then. Okay, I think I only have one more problem, and that's good because I'm really tired. And so draining a tank, an inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole in the vertex at a rate of 2 feet cubed per second. What is the rate of change of the water depth when the water depth is 3 feet? Hint, use similar triangles. Okay, so we're going to do this problem. So they have a cone is what they're having. And I don't know if you've ever been to one of those microbreweries, but they use conical shaped tanks. And so they kind of look like this. The first time I ever saw one was on a tour of Sam Adams in Boston. And then I've since seen them at a couple of, like, I think the one in Kernville has a conical tank in it too. Maybe Lengthwise does too. I'm not sure. Anyway, so this is what they have kind of going, and this is the drain, and so the water is draining out there at the bottom, and they're saying that the height of this tank is 12 foot. They're big, and so this is 12 foot, and the radius is 6 foot at the top here. And it says that the water is draining in the vertex at a rate of 2 feet cubed per second. So this is dV/dt is 2 feet cubed per second. We'll visit back, is that positive or negative, here in a second. And then they said, what is the rate of change of the water depth? And so you can see that, I don't know if, back to the rusty water, right? Because I have a purple pen, but here's the water depth, and a little bit later, the water depth is here, and a little bit later, the water depth is here. And so the depth is definitely going down, and that's what they're wanting me to find. Now, on a cone, um, the volume of a cone, the volume equals, is it 1/3 pi r squared h? I believe it is. Ooh, I hope I'm not wrong on that. Um, I wonder if I can make sure on my computer here, since it's right here. And I'm going to give that I'm really tired. Uh, volume of cone, but I don't want to make a mistake of cone. Yeah, it is 1/3 pi r squared h. So that's very, very good. And so what they're wanting me to find, the depth is h, is what it is. So they're wanting me to find dh dt when h is equal to 3 feet. And so that's kind of what we have kind of going. So now if I was to take the derivative right now, in my problem, I would have dv dt, which is fine because I know that that's 2 feet cubed per second. And I would have dr dt because the radius isn't a constant in this cone. Do you notice that the radius of the radius of the cone itself is 6 foot, but when we're talking about the volume here, we're not talking the volume of the cone. We're talking the volume of the water in the cone as it drains out, and so the radius is getting smaller and smaller as the water drains out of the cone, and the height of the water is getting smaller and smaller as it drains out of the cone. And in fact, because the volume is decreasing, this would be negative. And so anyway, so that's what we have going on. So the radius is not a constant like it was in the last problem. So we cannot put in any value for the radius, like 6 feet. Um, and um, and so because that radius is changing, and the height is also changing, so we couldn't put in 12 feet for the height. And we would get, when we take the derivative, dr dt and dh dt. Now it's fine to get dh dt because, well, we want to know what dh dt is. That's what they asked us to find. And but I noticed that when I read carefully through the problem that that dh that dr dt isn't mentioned. They don't want me to find it, and they don't tell me what it is. So if I take the derivative right now without getting rid of r, I will not be able to finish the problem because I won't have a value for dr dt and maybe r as well. And so here's how I'm going to get, here is how I'm going to get rid of that. They gave me the hint of using similar triangles. And so right here, this is 6 foot. Will this pink pen write? Yeah, not very good. And this was 12 foot. And this creates a triangle right there. 6 foot and 12 foot on the side. And then right here, this is the water height and the radius of the height and the radius of the water right here. I'm going to call that R, and I'm going to call that H, because that's really what R and H are in this problem over here. And so and because these triangles, they're on a right cone, they're similar triangles. So so we're going to be able to use R is to H as 6 foot is to 12 foot. In fact, R is to H of half. And then I want to solve for R so that I can get rid of R in this equation right here. So I'm going to multiply by H. So this will be R equals 1/2 H for this particular cone. So always the radius is half of the height. And so then we can put this in. I haven't getting in my work there. So my volume equals 1/3 pi r, which is 1/2 h squared h. I haven't found the derivative yet. I'm not going to find the derivative until I clean this up a little bit. 1/2 squared is 1/4, and h squared times h is h to the third. So, and remember that was 1/4, right? That's what I have here. And I'm going to multiply that by the 1/3. And so that's going to be 1/12. Is that okay? So the volume is 1/12 pi h cubed. And I haven't found the derivative yet, but now I'm going to find the derivative. So I'm going to find the derivative. With respect to time. So when I ask you one of these problems, I have points associated with that equation right there. And I always write, now I'm going to find the derivative so that everyone knows that I haven't found the derivative. And then I find the derivative. And so when I take the derivative of v, I get dv dt. 1/12 pi is a constant, so it holds still, times, and then the derivative of h cubed is 3h squared dh dt. So there I found the derivative. Then I'm going to plug in everything I know, right? And if you do that, you'll notice that you know dv dt. 1/12 pi is a constant, and 3 constant. H is also 3, coincidentally enough, squared. If I'm just thinking about my units, the units on dv dt should be feet cubed per second, right? That's what they say right here. H has the units feet squared. So dh dt should have the units feet per second. And so since I kind of figured out the units, I feel like, okay, the units on dh/dt are going to be feet squared. I feel like I can leave the units off since I've figured out what they're going to be. If I wasn't sure about that, I would just include them as what I would. But since I've kind of reasoned out what they're going to be, I feel okay with just putting in here -2 equals 1/12 pi times 3 times h, which is 3. That's where I got the feet squared, right? Squared, and then dh dt, which is what I'm trying to find. So when the dust clears here, I have -2 equals, and I have 1/12 times 3 times 9. I'm going to put that in my calculator, and I know that's going to be pi as well. So this is 1/12, 1 divided by 12, 1/12 times 3 times 9. 3 squared is 9. So that's 9/4. So this is 9 pi over 4 dh dt. And I want to solve for dh dt. So I could multiply by 4 and then divide by 9 pi. I could do it in 2 steps, or I could do it in 1 step by multiplying by 4 over 9 pi. You do you. I'm going to multiply by 4. So I'm going to multiply by 4. So when I do that, I get -8 equals 9 pi dh dt. So times 4 times 4. And then I'm going to divide by 9. So this is 9 pi. So this is -8 over 9 pi equals dh dt. And I kind of ran out of room and got here into the homework. And so I'm just going to put the units on it and put a box around it and call it done. dh dt equals -8 over 9 pi feet per second. And since they asked for the rate of change of the water depth, I need the negative on it to show that it's going down. Okay, so we did a lovely job on that. I'm going to stop recording, put this on YouTube, get in my bed, put it on Canvas, all those things. Try these homework problems. See if you can do them. I bet you can. And the answers are on Canvas.